Hello and welcome to this PIR live event webinar brought to you by Partners in Research Canada. My name is Stacey Joyce and I will be your host. If you're joining us live, remember that you can ask questions anytime by clicking the chat button in the top left corner of your screen. Just change that to field to all panelists and attendees. That way the other students who are watching will be able to see what questions are coming from the other classrooms that are joining us live. And it's my pleasure to introduce today's guest. We have Dr. Artur Izmaylov. He is an associate professor in the departments of chemistry and physical and environmental sciences at the University of Toronto. Thank you so much for joining us. I will turn it over to you.
All right, thank you for having me. And let me just put up my presentation. Can you see the presentation?
Not yet. I just need you to share your screen, I believe.
Okay. Right. How about now?
No, I don't. Oh, wait, there we go. It's loading up now.
Okay.
So I can see your screen. I just don't see the presentation yet. There we are. Perfect.
Right. Great. Hello, everyone. So today I'll talk about quantum technologies in the screens of your electronic devices. So probably you're all familiar with the electronic devices these days, the monitors, displays, iPads, iPhones. And it turns out that there is some interesting quantum physics that is going on while you're watching these movies from Netflix or doing other things. So I will demystify some of these aspects today, hopefully. So it turns out that if you zoom in into what is happening in your devices, it's all pretty much about interaction of molecules with light. And molecules there for a reason, because all the materials that constitute the screens of your devices, they usually use some kind of materials, and they have molecules in them. So molecules can be of different kind, and they all share one common thing, though, is that they have even smaller particles inside, electrons and nuclei. So electrons are negatively charged particles and nuclei are positively charged particles. So that's why they like to be together, they like to form molecules, all right? And this is what constitutes the material of your display and what is inside. Then the second component of the action, essentially, is other small particles. They are called photons, and they are particles of light. So whenever we have sun or our devices on, then we have light coming out of these devices, or we have light from sun. And so one thing we will need to know about photons is that they have different properties. One of them is color or energy associated with color. So you can think of photons as small particles that are running around very quickly, and they run with different velocities, different energy. So to see that, you can use glass prism to say split the white light that we have from sun or other sources into the rainbow. And the glass prism here works more like a running track, where the faster runners, say blue part of the spectrum, they have more energy. They spread from the other runners, which have maybe less energy, like a red part of the spectrum. Okay, so what we'll be talking today about is essentially interaction of the molecules with light. And turns out, to describe this accurately enough, you need a special science, quantum mechanics. It's the science about small particles, and it was invented back in 20th century by many scientists, and one of them is Austrian scientist Erwin Schrödinger, who came up with the main equation that describes interaction of different particles, describes any molecules. And because the equation is so general, he got Nobel Prize for it, right? Because it allows you to describe things generally and accurately. So, but the equation itself is relatively complicated. So I'm not going to go into the details of it because simply it's not the place and time. It's very important, but it is also very complicated. Actually, the second Nobel Prize winner in the same year, Paul Dirac, who was considering mainly the light part of the problem, he emphasized that quantum mechanics with the Schrodinger equation, it actually encompasses all the laws of nature to describe small particles. But the problem is that the equations that arise from that consideration, they are much too complicated to be soluble, right? So at this point, you may think if Nobel Prize winner thought that the equations are too complicated, then probably it's a kind of a stop sign for everyone, and we should not enter this area. And there is some truth in it, in this thinking, but also I want to emphasize that it was long ago, and so since 20th century, beginning of 20th century, things changed drastically, and we have more powerful computers which can help us to solve these equations. But there is a truth in this statement that we should not probably enter right now in this area because it's still relatively complicated. So in this talk, what I would like to do, I would like to simplify quantum mechanics for you so that you can understand some part of it and how it works for electronic devices and the screens, and how can we enjoy virtues of quantum mechanics in our real life. Okay, so it all starts with considering again electrons and nuclei, and noticing that electrons actually are 1,000 times lighter than nuclei. So as any lighter objects, they usually much faster than nuclei. So you can think of electrons as being like cats and dogs, and the nuclei being like elephants, for example, right? So the same ratio of masses. But it turns out that the electrons, they are even much faster than the cats and dogs, and they are running around. And better comparison would be with superheroes that you probably all know about from different cartoons like Flash, right? And what this analogy kind of provides us with is the picture where electrons are running like superheroes around the nuclei and form these clouds. Clouds because we don't actually see the electrons; they are so quick, but they want to be around nuclei because electrons are negatively charged and nuclei are positively charged. So there is this cloud around the nuclei that is always there. Usually, it's hard to decompose the molecules to separate electrons from nuclei, right? So this is going to be our main picture, that we have these electronic clouds, and turns out that different molecules, they can have different clouds. Like in nature, we have different clouds, right? So there are some clouds which don't even pour rain, or there's rainy clouds, or there are thunderstorm clouds, right? So the same with molecules. Each molecule can have different electronic states, and those states correspond to different trajectories of our superheroes running around the nuclei, right? And it turns out that these different clouds within the same molecule, here on the left I have a benzene molecule, one of the most beautiful molecule out there, which has a high symmetry, right? So there are different clouds, and they have all somewhat different energies because well, electrons are moving differently in those clouds. And when light comes into interaction with molecule, it turns out that light, say if we have a red light coming in, it can actually promote or make electrons run faster and promote the system from state which I denoted here as E1 to the state E2 by changing the cloud of electrons, right? And if the kind of more powerful light comes in, like a blue light, then it can promote, say, molecule from E1 to state which is higher than E2, E3 state. And as you can follow this analogy with the natural clouds, I put the thunderstorm cloud close to E3, and that was for the reason because some clouds, they are like thunderstorm clouds, and we know that thunderstorm clouds, they can produce lightning, right? So in the case of molecules, this state E3, for example, can produce light back. So it essentially can produce lightning and deactivate the system back to the ground state, so to the cloud which we started with, right? So this pretty much is the simplified version of quantum mechanics and how molecules interact with light, right? Because light essentially makes the changes in the electronic clouds of molecules. Now, how is this all related to the electronic devices? And today I would like to just quickly show you two technologies which are very common in our devices. It's liquid crystal displays, and the second one will be light emitting diode technology. And so they all will be using pretty much the same theory that I just explained to you with electronic clouds and light interacting with it. So let's start with liquid crystal displays, LCD. So Apple company uses LCD technology a lot. So it's implemented in iPhones and iPads. And the way it works, if you cut the display perpendicular, right? So if you look at the layers that form the display, so it all starts with a left layer, which provides the backlight. So this technology uses the external light, like a lamp out behind the screen. And so there is also a middle layer that does some transformations with light. So this middle layer, the core of the technology is liquid crystals. And so that's the middle layer. So what liquid crystals allow you to do is you can manipulate with the position of liquid crystals and make light either go through or not go through, right? So, and if it were the whole technology, then we would see black and white spots. So where the light went through the liquid crystals, we would see the white spots, and where light was stopped by liquid crystals, then we would see black spots. But of course, to see the colorful pictures, what this technology also have is color filters, right? So color filters are essentially spots of the different color, and they essentially can light up if the light goes through, or if the liquid crystals don't allow light to go through, then these pixels will be just dark. And say in this area, for example, light went through the blue one, and that's why we see blue pixel, while the red and the green, they are dark. And then in this area, again, the blue, in this area, the green one was light up. And so that's how we get colorful image. So in simple, actually, this technology a lot like stained glass that we all very familiar with, and just want to emphasize how the stained glass works. The way it works is pretty much we need to remember that our light is a white light again, but what stained glass does to white light, it has chemicals in different spot of the stained glass has different chemicals, and some of these chemicals absorb part of the spectrum. So say if the light comes through the blue area, then it means that the red part of the spectrum is absorbed by chemicals. And so at the quantum level, again, this chemical would correspond to a molecule that has the different electronic clouds, and the light, say red part of the spectrum, is absorbed, so the blue part of the spectrum is kind of going through, and we see it. So that molecule essentially looks blue to us, and it makes the light which is coming through the stained glass blue. And the different molecule could have absorption in the red region, and then the light that goes through, in the blue region, and then light goes through is in the red region. So then we see the red regions in the stained glass. Okay, so that's a liquid crystal display technology, which is very similar to stained glasses. And another technology which Samsung company uses a lot is so-called light emitting diode technology. So the way this technology works is a little bit different, because here at the lower part of the presentation we have the device cut into pieces, and the most important part is this organic emitter material in between the two electrodes, sandwiched between the two electrodes. So this technology essentially put the molecules in between the two electrodes and zap them with the electricity. And so what happens when you do that, if you find the special molecules, then when you zap them with electricity, the positive and negative charges recombine on the molecule, and what it does, it excites the clouds again of the electrons in the molecule, and you essentially end up with the excited states of the molecule. Those clouds, they can produce light, and that's how this thing works. If you have a molecule that has an excited cloud which is high in energy, then it emits the blue light. If it's lower in energy, then it emits green or red light, one of those, right? So, and that's how essentially light emitting diodes work. You add electricity, and electricity essentially through molecules produce light via emission. So what's next? Here I just summarize pretty much the technologies that we had from old days. In the left, this TV screens that you probably haven't seen even. Then we're going in time to the right, and these days there are prototypes of screens which are bendable, very light, very safe for the environment, and can be recycled, and they can last longer. So all that is possible because chemists, physicists, and computer scientists, they all work together to come up with different chemicals that allow to synthesize molecules which are more efficient emitters, and they last longer, and they are safer for environment. That's pretty much where things are moving. There are still problems, for example, with blue light, because it's a high energy transitions. When say organic compounds like the ones at the bottom are excited, and they're supposed to produce blue light, various molecules that are around, oxygen, for example, water, they make these molecules to degrade, and that reduce the lifetime of the device, and that's some of the current challenges of the technology that scientists are working for. All right, that ends my presentation. I'll be happy to entertain any questions you guys have.
Well, thank you so much for those explanations. I didn't realize that we had different technologies being used primarily by different hardware producers, like Apple sort of choosing one and some Samsung devices with the other, etc. Because to the naked eye, they look the same.
That's right. That's right.
So is there a distinction here? Maybe I'll just start out with a question about quantum physics versus quantum chemistry versus quantum computing. These are all different titles that we hear sometimes. Is there a distinction between those two or three areas?
Right, there are certainly distinctions, mainly related to the areas that this core science, quantum mechanics, is applied to. All right, so, and the goals are also quite different. So let me start with something that is closest to my research, quantum chemistry. So quantum chemistry is essentially science that uses principles of quantum mechanics to figure out what the properties of molecules will be based on the structure of the molecule, right? So this is a non-trivial task, because even if you know the structure of the molecule, you don't know what color, for example, this molecule will be, and what light it will absorb, whether it can be used as an emitter of light in a light-emitting diode. So those questions that can be addressed with the methods of quantum chemistry. Now, quantum physics has a slightly different focus. It's mainly interested in, like, say, materials, like periodic systems, not the small molecules. Molecules are usually of interest to chemists, right? Also, physicists are more interested in atoms still. And, well, there are other areas like You also mentioned quantum computing, for example. That's an area where we try to use quantum mechanical principles to speed up our calculations. So to come up with this quantum computer device that works better and faster than the classical computer, right? So the unifying theme of all these areas is quantum mechanics, and if you learn quantum mechanics, you can actually go and do something useful in these areas. But of course, there is a lot of material, so already people build up in these areas because they were working towards certain goals, and the goals were somewhat different in these three sciences. Okay.
So do you find yourself participating in collaborations in your work and your research?
Yes, somewhat, because my research is mainly theoretical and computational, so we mainly predict things based on paper and pencil or computer simulations. And of course, there are lots of the equations that I just showed you a little bit. The Schrödinger equation is very difficult to solve, and we need to do some approximations, so it's usually useful to have some experimental feedback, essentially showing that, okay, this type of approximations are still adequate for the systems that we are interested in, or maybe we can do even more drastic approximations and still we still within the experimental boundaries of what is reasonable, while well, maybe that's not the case. So it's always useful to collaborate with experimentalists and see and learn something about the real systems, because what we are considering, it's somewhat a model of the real system, and the reality check that we're getting through these collaborations is very useful.
And so a more specific question now we have coming from Brentwood College in British Columbia, wondering how soon we will have a TV screen that we can roll up. What do you think?
Well, the prototypes are also, well, not for TV, I guess, but mainly for smartphones. Prototypes are, they do exist, and they already been advertised, but it's, I guess, certainly a question how scalable the technology is, and how much like how to make it cheap enough, right, so that the consumers will buy it, right? That's unfortunately is outside of my expertise. Because
yes,
no, it's coming. I would just say that it's coming.
Yeah. It's always difficult to predict these
That's
things,
right.
because
That's
some of the experiments work wonderfully just like the models, and as you said, you do that reality check because they don't always work exactly as modeled. Next up, we have a question about how quantum computers work.
Mm-hmm. Oh, that would be a separate lecture, I'm afraid, right? But also going the kind of below the surface, or explaining it relatively well, would require audience to know some basic principles of quantum mechanics. And of course, you may have heard those principles like superposition, entanglement, but having some practice with those notions would be useful to understand like if I start explaining how quantum computer works. So, but in a nutshell, what quantum computer can use is essentially parallelism. So it can do it can calculate certain things at the same time simultaneously, and then in a classical computer, you would need to do the calculation of, say, one function in for one value, the same function maybe, or a different function for another value. So those would be a separate calculations, while quantum computer would allow to calculate all these functions at the same time. So that's the quantum speed up. Now, it turns out that practically there is still a challenge to retrieve the results of those calculations, So it turns out that the quantum computer can calculate them at the same time, but when you do so-called measurement to understand what is the result, well, then quantum system usually collapses to one particular value, and then there is no use out of this simultaneous calculation. So that's where quantum computer science, I guess, would be useful, because they devised algorithms where you don't need to, well, you first generate the result, do the manipulations, and then you don't lose that speed up by doing the measurement. But of course, this, I don't want to go too much into the details, because I don't think that it will make much sense if the audience is not prepared for the explanation of quantum stuff. Yeah.
You're sending me back in time in my memory to some lectures about Schrodinger's cat.
That's right.
So if anyone out there is really curious, just Google Schrodinger's cat and see what you can find.
Unfortunately, with the Schrodinger's cat, there is not. I don't think there's a good explanation of that. I thought about this myself for some time, and actually, there is a simple explanation. Okay, there is a simple explanation which everyone can understand. So the result that they arrived at, the Schrödinger cat can be alive and dead at the same time, seems like a result that is puzzling or counterintuitive. But then what helps actually is thinking about for how long Schrödinger's cat can be in that state of alive and dead at the same time. And if the answer to that question will be less than I don't know, time that electron, it takes electron to orbit around the nucleus, so very small amount of time, like 10 to the minus 17 second, then who cares that it stays in that state for 10 to the minus 17 second? If this state of being alive and dead at the same time is very small in time, then it really is not that puzzling. So you can think of that way. Time kind of makes somewhat a resolution in this paradox, that if this weird state is only for 10 to the minus 17 second, then it's not that bad. You won't notice it in real life, right? So because we do not detect phenomena at this time scale, right? So for us to detect that, oh, something is wrong with the cat, it's in the state of alive and dead at the same time, we would need probably a couple of seconds to realize that something is wrong.
I have never heard this problem described this way. It's definitely something that dwarfs the rest of the issue, that it ultimately may not matter.
Right. So, but then you may ask, of course, more profound question: why is it that small objects like atoms, they can be in this superposition state? Superposition state is a quantum language for the being alive and dead at the same time, in the case of cat, right? So being in two states at the same time. So why small systems can be put in such a situation, while when you go to the bigger objects, the time that you can conserve the system in this simultaneous state of being alive and dead, it just shrinks tremendously. And that's one of the problems with quantum computer, because quantum computer was incepted probably by Feynman back in beginning of 20th century, or somewhere in the middle of 20th century. But practically to do it takes a lot of efforts, because you want to put system in these states of being at the same time in, well, alive and dead, figuratively speaking, for a long time, because you want to do calculations during that time, and keeping the system which is big enough in this simultaneous state is challenging technologically.
Right. Well, I do want to take us away from the very specific questions before we have to end things today, and ask you a little bit more generally, if we have any audience members who, find this very interesting and might want to pursue whether it's quantum physics, quantum chemistry, quantum computing, quantum something else we haven't started yet. What would you suggest to them? Maybe using your own career path as an example, and any advice you might have.
Clearly, to understand these things, not on a superficial level, but actually be able to, well, come up with some new ideas and do something that's I think is very rewarding. You need the math background, because mathematics is essentially a language that computer scientists or physicists or quantum chemists, they all share that one language, and that makes the communication, collaboration, and further progress possible between these disciplines, because they all share this one language, mathematics. And studying math, and that was useful for me, and was like, I could highly recommend that. But this is too general, I understand. One thing I realized that we don't do a lot in our education is making sense of things. Like there is a high pace of education now, that we're trying to put more and more information in the heads of students. And I think this is counterproductive, especially with math. Math has this image of being difficult, being non-intuitive, but instead it's the way, if you go to the history of math and see how the concepts were introduced, it's always very natural. It's just, if you take it slowly and actually explain why did people come up with addition, multiplication, integration, differentiation, all that stuff. So why one way of doing things makes sense and another way doesn't make sense, that would be more productive, because I think it would take things slower, but people would understand rather than memorize things. Okay, and that is very important. So for students, I would suggest try to make sense of things that the teachers are teaching you at school, and try to engage common sense and see how this all is making sense.
And so how did you find your way to this career? Did you always know you wanted to study quantum mechanics, or did you start in a different path and make a few turns?
So I generally was fascinated with chemistry, mainly because of fireworks and other things which are loud and don't always smell good, right? So just chemical experiments are always fascinated me, I guess, because there are lots of effects, interesting effects. And that's how I came to chemistry. But then at some point I realized I want to understand more than just keep doing the interesting experiments. I want just to maybe predict what's going to happen, or to understand why is this happening. And that's how I started drifting towards more theoretical chemistry and physics and math. That became kind of more interesting for me at some point. Right. Rather than just spending time in the lab, but that was my path.
Wonderful. Well, that is all the time we have. Thank you so much, Dr. Izmaylov, for taking the time to discuss quantum technologies with us today.
No problem. Thank you.
And next week on PIR Live Event, we are discussing functional foods and their effect on our health. More information about this webinar and other PIR educational programs is available at pirweb.org. Thanks so much for tuning in, everyone. Have a great day.